I think now it should be okay. Right? Can you give me feedback if it is, if the audio is clear now? Is it okay now? Manoj, Soumithya. Okay. Yes, I believe the audio is clear now. So let me continue. So sorry for the interruption. There was some mistake in the settings. Yeah. Right. So this is the A modulated signal equation. So if you plot the spectrum of the signal, AC cos, let me expand this just for better understanding. AC cos omega ct plus Ka AC m of t into cos omega ct. See this one, just these two terms I've just expanded and written it. Now, if you plot the Fourier transform of it, S of f AM signal, frequency, Fourier transform of AM signal is Fourier transform of AC cos omega ct is AC by 2 into, I'm taking the Fourier transform of cos del of f minus fc plus del of f plus fc divided by 2. Divided by 2 I've written here already. Plus Ka AC m of t Fourier transform is m of f. When m of t is multiplied with cos omega ct, this is called as modulation property in Fourier transform. So I'm just trying to find Fourier transforms. So Fourier transform, this part, m of t multiplied with cos omega ct is m of f minus fc plus m of f plus fc divided by 2. So this is the Fourier transform of AM modulated signal. AM means when somebody says just AM, they are talking about Ssbsc, double sideband full carrier. There are other AM modulation techniques also, but if they simply say just AM, okay, they talk about the basic amplitude modulation technique, which is double sideband full carrier modulation technique. Okay, now let us quickly plot the spectrum. Let us quickly plot the spectrum. If m of t has a Fourier transform of some spectrum, some shape of the spectrum. Let me take it as a triangle spectrum. It can have any shape. Okay, message Fourier transform can have any shape minus b2 plus b as a function of f. Fourier transform is m of f. That is a notation that we generally take for Fourier transform, which is the capital letter. Right. So why did I plot it as a symmetric spectrum? Why did I plot it as a symmetric spectrum? The reason is because message signals are assumed to be real. All practical messages are real signals, which means they take only real amplitudes. They take real values. At every point of time, they take only real values. For real signals, real in time domain, in frequency domain. In frequency domain, they will be conjugate even symmetric. They will be conjugate even symmetric, right? So that is a very basic property of Fourier transforms. Okay, what is the meaning of conjugate even symmetry? Meaning of conjugate even symmetry is magnitude spectrum. This means modulus of this magnitude spectrum is having even symmetry, and the phase spectrum, meaning of conjugate even symmetry is both of these things are happening. Magnitude spectrum is even symmetric and phase spectrum is odd symmetric. Okay, so sir, did we plot the total spectrum here? No. If m of t is real, m of f can be complex. If m of f is complex, any complex signal, how do you plot it? You have to plot the magnitude spectrum separately. You have to plot the phase spectrum separately. So we are generally interested in magnitude spectrum. Unless a problem demands phase spectrum, we generally plot only magnitude spectrum. So though I'm writing it as m of f, but basically what I'm plotting is only mod m of f. You can assume it is mod m of f. Okay. So magnitude spectrum will be even symmetric, not the total spectrum. Total spectrum is conjugate even symmetric. Only the modulus part of it or the magnitude part of it is having even symmetry. Generally, you observe in any situation, generally in all analysis, we'll take it as even symmetric magnetic spectrum. Though they write it as m of f, they are talking about mod m of f. Okay, right. So here I have recollected some basics regarding Fourier transforms. So when you study that Fourier transform, if you are not comfortable with Fourier transform, then these things might look like tricky for you. But if you are comfortable with Fourier transform, these things are easy stuff. So don't worry if you are not getting these things completely. Your basics of Fourier transform might not be very good. Okay, you can go through Fourier transform later, and then you'll look at these things as easy things. Fine. Now let me come back to the modulated signal spectrum. S of t AM signal. What is the Fourier transform of this one? S of t AM signal. S of t AM signal. Fourier transform is S of f AM. How does it look like? Let us plot it. Let's plot it. You can try plotting along with me. Start plotting along with me. S of f AM signal. Come on, plot it along with me. So we know S of f AM signal. Mathematically I have written it. Let us plot that. So del of f minus fc means del of f is impulse at 0. Del of f minus fc means impulse at fc. Impulse at fc. Okay. Next, del of f plus fc means impulse at minus fc. Next, m of f minus fc. M of f we know. M of f minus fc means m of f shifted to fc, shifted towards right side by fc. This one shifted towards right side by fc. This 0 will go to fc and b will go to fc plus b. So this total thing will get shifted by fc. So after shifting, this is how it looks like. This is m of f minus fc. Next, m of f plus fc means m of f shifted towards left side by fc. So this will be fc plus b, and this is fc minus b. This is minus fc plus b, and this is minus fc minus b. So what is the bandwidth of the signal? The question that is asked in the previous one is bandwidth of AM modulated signal. So I've given basics, a little bit more basics than what is required for answering this question. So what is the bandwidth of the signal? It is 2 times b. What is b here? B is bandwidth of the signal, bandwidth of m of t. Bandwidth of message is what is the bandwidth of message? It is the highest positive frequency present in the message. The highest positive frequency present in the message is b, or the range of positive frequencies present in the message is b, right? So if you know bandwidth of message, bandwidth of AM modulated signal, S of t AM or S of f AM signal is 2 times bandwidth of message. 2 times bandwidth of message. What is bandwidth of message? Bandwidth of message is nothing but the range of positive frequencies present in the signal, or the highest positive frequency present in the signal, right? With that understanding, let's go back to the question. So right, so what are the frequencies present here? Let us plot the spectrum of the signal here. The carrier frequency is 600 kilohertz, which means there is an impulse at fc, which is fc 600 kilohertz here. And they are also saying that there are other frequencies in AM signal. What are the other frequencies? Apart from carrier frequency, what are the other frequencies present? The other frequencies correspond to message. Other frequencies correspond to message, and the frequencies are at 610 kilohertz, 620 kilohertz, 630 kilohertz. This is 610. This is 620, and this is 630, right? Now tell me this, whatever frequencies are present above fc, whatever is the shape that you're seeing above fc, same shape are we seeing before fc also? The spectrum is symmetric with respect to fc also. The spectrum is symmetric with respect to 0 also, correct? Whatever shape you're seeing right side of fc, the same shape you should be seeing on the left side of fc. It should be symmetric with respect to fc, right? If it is symmetric with respect to fc, whatever frequencies you are seeing on the right side of carrier frequency, same frequencies you should be seeing on the left side of fc. So if there is a frequency at 610 kilohertz, what is the symmetric frequency with respect to 600? There should be a frequency at 590 kilo. So I'm not trying to only figure out the answer for this question. I'm trying to do the total analysis, which might help you to answer a little bit more difficult questions also. Right. Next, what is the symmetric spectrum corresponding to 620? With respect to 600, 620 is at a distance of 20. So what is the impulse at a distance of 20 on the opposite side? An impulse at 580. 580 and 620, these two are symmetric because they are both at the same distance from 600 kilohertz. Next, 630, this impulse is at a distance of 30 kilohertz from the carrier frequency. So which means on the opposite side, at a distance of 30 kilohertz, what is the frequency? It is 570 kilohertz. Sir, impulses height, you are changing. See, we don't know the amplitude of the impulses. We don't know the height of those impulses or area of those impulses because there is no such information given. Just for the sake of showing you the information, whatever information we know, I'm showing. These area of these impulses, we don't know them. So that's why I've taken whatever amplitudes I like to take. But if you want, you can plot with the different heights also, no problem. Right? And one more thing is the spectrum is symmetric with respect to y-axis also, right? So which means the same thing will be here also. Impulses here and 3 impulses here. Okay, minus 600, minus 590, minus 580, minus 570, and here minus 610, minus 620, minus 630. Okay, so I believe you have understood how to plot the spectrum. Now, what is the bandwidth of AM modulated signal? It's the range of positive frequencies. What is the range of positive frequencies? Bandwidth is the range of positive frequencies or the highest positive frequency minus lowest positive frequency. What is the highest positive frequency? It is 630 kilohertz. Minus what is the lowest positive frequency? It is 570 kilohertz, which is equal to 60 kilohertz. I've plotted the spectrum just for your better understanding, but if you ask me to answer the question by looking at this, I'll answer it. The reason is other frequencies present in AM are 610, 620, 630. From this, I will understand that frequencies in the message. What are the frequencies in the message? Whatever are the frequencies in the message, they are getting shifted by FC, no? Correct or not? See this one? Whatever frequencies are there in FC, all of them are getting shifted by FC, no? Which means this is FC plus 10, this is FC plus 20, FC plus 30. So what are the frequencies in the message? Original frequencies in the message are 10 kilohertz, 20 kilohertz, and 30 kilohertz. Correct? These are the frequencies in the message. Is it correct? So what frequencies are there here in the message? From the question, there are 610, 620, 630. 600 is FC, 610, 620, 630 are present, which means here it is 10, 20, and 30 are present. 10, 20, and 30 are present means minus 10, minus 20, minus 30 are also present. Correct? So here the frequency is present at 10, 20, and 30. What is the highest frequency in the message? 30. 30 is the highest frequency. What is the message bandwidth? 30 kilohertz. So 2 times bandwidth of messages, bandwidth of AM modulated signal. So 2 times of bandwidth of message. What is bandwidth of message? Just now we have figured out. There are 3 frequencies in the message, 10, 20, and 30 kilohertz. 30 is the highest. 30 you can substitute here. 20 into 2 into 30 is 60 kilohertz. See how easily we can solve the question. So from this information, we can figure out bandwidth of message. Just to solve this question, you can analyze in this manner. That is sufficient. But why I have told you all this stuff is just for the sake of analyzing some tougher questions. This process of analysis will help you to solve tougher questions as well. So bandwidth of AM signal. Bandwidth of AM signal is 2 times message bandwidth, which is 2 into 30 kilohertz, which is 60 kilohertz. I hope you are following. Is it clear till this point? Any doubts till this point? Come on. If there is any doubt, anything you want me to repeat, quickly tell me now. Let me know if you have any doubts. Shall I move on to the next question? The spectrum analysis, okay, analyzing the frequency domain of any modulated signal is very, very important. From easy questions to very difficult questions also can be framed in this topic, in this area. For every modulation, plotting the spectrum, analyzing the spectrum is very, very important. Okay, right. So how about the next one? Same data, but the question I'm asking you is different. Now you'll understand why I've done some analysis in the previous question, which is more than what is required for that question. Same data. An AM modulated signal whose carrier frequency is 600 kilohertz has frequencies 610, 620, 630. Find the remaining frequencies present in the AM modulated signal. Find the remaining frequencies present in the AM modulated signal. What are they? Can anyone answer? 600, 610, 620, 630. This is FC. This is FC. FC is 600 kilohertz. The other frequencies, the frequencies present are 610, 620, and 630. These are the frequencies given: 610, 620, 630 kilohertz. Right? Now they're asking us to find the remaining frequencies present in the AM modulated signal. Recollect, what is the behavior of AM modulated signal? Recollect, I'll show you. See here. M of f, this is M of f. M of f is shifted to FC. So whatever spectrum is present above FC, same spectrum is present below FC also. Whatever is the shape above FC, same shape is present below FC also. Or whatever frequencies are present above FC, symmetrical frequencies are present below FC also. Right? So the symmetric frequency, whatever is the shape present above FC, same shape should be present below FC also. So there will be symmetric frequencies to these three frequencies. Okay. Or I can also analyze it this way. So if this is the spectrum of the modulated signal, AM modulated signal, partial spectrum, what would be the spectrum of message? 610 kilohertz is because of shifting the spectrum of message by 600 kilohertz, correct? How did we get the spectrum? Message spectrum shifted towards right side by FC, we get this spectrum, correct? So we get this spectrum because of message spectrum having a frequency at 10 kilohertz, impulse at 10 kilohertz, getting shifted by 600, we get this one. How do we get this one? Because of message having an impulse at 20 kilohertz. How do we get this one? Because of an impulse which is present at 30 kilohertz, shifted towards the right side by 600 kilohertz, we get this, right? But in message, we have symmetrical frequencies, which means because of 10, whenever there is 10 kilohertz, there will be minus 10 kilohertz also. Why? Because I have discussed the basic in the previous slide. Because we talk about real signals. For real signals, magnitude spectrum is even symmetric. Next up, if there is a spectrum frequency at 20 kilohertz, there should be a frequency at minus 20 also. If there is a frequency at 30 kilohertz, there should be a frequency at minus 30 kilohertz also. Right? So this total thing is shifted towards right side by FC. What happens? These frequencies also will be present here. So minus 10 kilohertz shifted by 600, it is 590. Or for this impulse, the symmetrical one with respect to 600 is 590. And for this one, symmetrical one is 580. Because this gap is 20, this gap also should be 20. Or minus 20 shifted towards right side by 600 kilohertz, minus 20 plus 600 is 580. Okay, next, minus 30 kilohertz shifted towards right side by 600. Minus 30 plus 600 is 570. Okay, that's it. We got the answer. So same impulses will be there on the negative side also. We don't need to plot the negative part. So whatever frequencies are here, same thing will be present here also. Right, now the question is find the remaining frequencies present in the AM modulated signal. What frequency they have given us till now? 600 they have given us. 610 they have given us, 620 they have given us, 630 they have given us. Find the remaining frequencies. What are the remaining frequencies? 590, 580 and 570. 590, 580 and 570. So option C, if you see, 590, 580, 570 are there, but 600 is also given. But the question is only find the remaining frequencies. 600 is already given. They told that it is carrier frequencies. So that's why the best option possible here is option D. Very good, Sai Charan. Any doubts till this point? Okay, I'm moving on to the next question. Name signal whose carrier frequency is 500 kHz, has frequencies 460 kHz and 480 kHz. Now, just looking at this information, first statement, can you quickly plot the spectrum? Can you quickly plot the spectrum of AM signal? Say, I've not taken the easiest questions. I'm taking slightly tricky questions. There are very easy questions also possible from this topic, but I have not taken them because easy questions anybody can solve. So this is 500 kHz. There is a carrier frequency at 500 kHz, and other frequencies present are 460 and 480. 480 is one frequency, another one is 460. This is 480 kilo, and this is 460 kilohertz. Same thing on the other side also will be there, right? Now, can you tell me what are the other frequencies present here? This is FC, and only the left side of FC is given. On the right side also same spectrum will be there, symmetrical spectrum will be there, correct? So could you tell me what are the other frequencies present? Or you can also figure out it this way. Why did we get these impulses? We got these impulses because of the impulses at minus 20 and minus 40. Minus 20 kilohertz, minus 40 kilohertz. This is m of f. M of f minus fc. We're talking about this is nothing but m of f minus fc. This is m of f minus fc. So we got these impulses because of m of f having impulses at minus 20 and minus 40. But m of f will be symmetric with respect to y-axis. So we should be having impulses at 20 kilo and 40 kilo as a function of f, right? So the other frequencies present are 20 and 40. So if somebody asks you the other frequencies, the frequencies present are 520 and 540 also. So though the question is not asked, I will answer. When I'm practicing, I'll answer this question also. Whatever possibilities I can analyze in that question, I'll analyze. So what is the bandwidth? It is 40 on this side and 40 on this side, or 540 minus 460 is 80 kilohertz. 80 kilohertz is the bandwidth of AM signal. Fine. What is effective? The effective modulation index of AM signal is 50%. What is the meaning of effective modulation index? Okay. So they are saying that mu is 50%. Mu value is 0.5. Mu multiplied with 100, they'll say in terms of percentage. Mu basically is a value generally which is taken as less than 1. That mu generally, if they are saying in terms of percentage, they are multiplying the mu value with 100. So 50% means it is 0.5. So find the ratio of power at carrier frequency to total power. So this is an easy question. So whenever they are asking the ratio of powers, then deal it like this. Power requirement in AM signal, it is given as PC into 1 plus K square into PM. PM is nothing but message power. I'll just recollect it once again. The power here is AC square by 2. You can also write as 2R if you are if they're saying that if this signal is transmitted through an antenna of resistance R, then you can write as AC square by 2R. What is the power here? It is K square AC square. Power in the message is PM, and power in this just cos omega t is 1 by 2. So it becomes K square AC square by 2 into PM. If they're talking about resistance of antenna is R, you can write as 2R. So total power in AM signal is AC square by 2R. That part is common in both the terms. 1 plus K square into PM. That is what is the power in AM signal. This is the power in AM signal. And only in the carrier, the power is AC square by 2R. So you can rewrite this as PC, carrier power, into 1 plus K square into PM. Okay. Right. So that's why I've written this formula. PC into 1 plus K square into PM. So let's divide this into two parts. PC plus PC into K square into PM. So this formula is valid for any message, general message with any number of frequencies. Since I can observe that message is having two frequencies, so it's not single tone modulation. Single tone modulation means only single message frequency should be there. But here there are two frequencies in the message. When there are more than one frequency, it's not single tone modulation. So we have to use general formula. So if it is 1 plus k square into pm, it's a general formula. Otherwise, it will be 1 plus mu square by 2. 1 plus mu square by 2 is a single tone case formula where message has only one frequency. Now they're asking us to find ratio of power at carrier frequency PC divided by total power PT AM. This ratio they're asking, ratio of power at FC, power at carrier frequency, to total power. So which is PC, I'm writing it as just PC only, divided by PC into 1 plus k square into PM. PC gets cancelled. So this ratio is 1 by 1 plus k square into PM. Okay, so that is the general answer. But here there are single frequencies. There are single frequencies means it is sinusoidal signal only, right? It is sinusoidal signal only. When it is sinusoidal signal, if it is sinusoidal signal, you can use the formula not only for single tone case. If it is sinusoidal, we can use the formula of 1 plus mu square by 2, but it should be mu effective square. Modulation index is effective modulation index of both the sinusoidal signals, 460 kHz, 480 kHz. There are two sinusoidal signals here with two frequencies. So if it is a single tone signal, it is mu square by 2. If it is two sinusoidal signals, then it is effective modulation index. So then PC divided by total power is equal to, it is 1 divided by 1 plus mu effective square divided by 2, which is 2 divided by 2 plus mu effective square, and we know what is mu, it is 0.5 or 1 by 2. So 2 divided by 2 plus 1 by 2 whole square is 1 by 4, which is equal to 8 by 9. The answer is 8 by 9. Very good, dreamer. Shall we move ahead? So if the message is not sinusoidal, then you have to use this formula. They should have given some other data to have these values Ka into P, Ka square into Pm. We can figure out with other information. Because it is sinusoidal, we are able to write it like this. If it is not sinusoidal, then we have to go with this formula. They would have given some other information to solve this question if it was another message other than sinusoidal message. Okay. Right, I'm moving ahead. Right. Similar question about ratio of powers. An AM modulated signal whose carrier frequency is 800 kHz. I'll quickly plot the spectrum. Carrier is 800. Spectrum has frequencies 760 and 780. 780 and 760, which means there are frequencies at 820 and 840. Okay, which means you can figure out the bandwidth, which is same as 80 kHz, same as previous one. The effective modulation index of AM signal is same modulation index also, 0.5 or 1 by 2. Ratio of power at carrier frequency divided by ratio of power at carrier frequency to power at 760 and 780. What is the meaning of 760 and 780? It is lower sideband, correct? This is sidebands. This is also sideband, which means sideband means we're talking about message, only the message part. So this is upper sideband, we call it. Lower sideband plus upper sideband together we call it as message. Okay. So they are saying ratio of power at carrier frequency divided by ratio of power and carrier frequency divided by ratio means division, power at carrier frequency by power at 760 and 780. Convert that into our language. What are they talking about? What power they are talking about? Power in the message. 760 and 780 means they correspond to message, but message means there are frequencies in the message at 820 and 840 also. So exactly speaking, they are talking about power in only the lower segments. Only the lower segments. From the question, try to convert it into our understanding. So we have this language, use this language of lower sidebands and upper sidebands. So they are talking about power, they are interested in the power of only lower segments. So this ratio they are asking us. So PC divided by, what is the power of lower sidebands? Let us quickly write the formula. PT is 1 plus PC into 1 plus mu square by 2 or mu effective square by 2 because it is a multi-tone modulation. Because it is sinusoidal, I'm taking it as mu square by 2 formula. Otherwise, I would have taken Ka square into Pm. So carrier power is Pc mu square by 2 into Pc. So this is sideband power. This is sideband power. Sideband power means it is lower sideband power plus upper sideband power together. Lower sideband and upper sidebands are equal and equal. They'll have equal powers. So lower sideband power or upper sideband power will be half of this total sideband power. So this is carrier power. Sai Charan, good question. How to find if it is sinusoidal or not? See, in this question, they're saying exactly 760 kilohertz is there. Correct? If they're saying only 760, which signal has only 760 kilohertz? Is there any signal other than a sinusoidal signal which has 760 kilohertz? Take any signal, any signal has lot of frequencies, not single frequency. Only this signal, let me write it, cos of 2 pi 760 kilohertz into t. If you plot the Fourier transform of this one, it will have impulse at 760 kilohertz and minus 760 kilohertz. Anything other than sinusoidal will not have a single frequency, single positive and single negative frequency, but many other frequencies. Yeah, sure, sure, man. I'll write it slightly bigger. Yeah, the reason why I'm writing smaller ones is because all the information is here. So if I write it here, if I write it in a different page, I have to scroll back to this page again and again. So then it will be difficult for you to understand. So that is the reason why I'm trying to compress the text size. But anyway, I'll try to write it slightly better. Okay. So is it clear, Sai Charan? When there is a single frequency, you can understand that it is sinusoidal without any confusion because there is no other signal which has that. Or the other one is e power j 2 pi 760 kilohertz into t. This also has single frequency, but this is not a real signal. This has only one frequency and that is at 760 kilohertz, whereas this one has frequency at 760 and minus 760 also. Okay, Sacharan, still not understood? If you can respond quickly, I can help you better. Right, so now let's come back to the question. Power in lower sidebands is half of this. What is half of that? Mu effective square divided by 4 into Pc. Pc gets cancelled. It is 4 divided by mu effective square. So 4 divided by, what is mu effective? It is half square is 1 by 4. How much is that? 16. Did you get the same answer? Answer is 16. Fine, I hope it is clear till this point. Can I move on to the next question? Right. This should be an easy question, but the next one with the same data would be slightly tricky question. First, let us answer this question. DSP signal S of t with full carrier. So what they are saying is they are giving us DSBFC signal, double sideband signal with full carrier. So they are giving us DSBFC signal or AM signal, you can say, is shown in the figure below. So an AM signal is given here or DSBFC signal is given here after modulation. So this one, this is what is AM signal. Okay, this is AM signal. This is not AM signal. Okay, this is just envelope. I should have plotted this in dotted form. Okay, this is not the actual signal. This is not the actual signal. This is just the envelope. Only all the peak amplitudes joined. This is how the shape looks like. Right. Now they're asking us to find the modulation index of the AM signal. AM modulation signal has modulation index, right? So yeah, let us recollect our basics. Peak amplitude of AM signal is given by AC into 1 plus mu, correct? If you are not sure, we can just write the equation first. We can easily recollect it. So we can observe that. Can you understand that the message is sinusoidal here? Are you able to understand that the message is sinusoidal? See this one, the envelope. In the envelope message we have, and you can see the shape of the envelope is sinusoidal. And it is a single tone modulation because only single sinusoidal signal is there. No complexities here. Is that okay? From seeing the shape, in the envelope we have sinusoidal message. It is very clear that it is sinusoidal. Message is sinusoidal. If message is sinusoidal, the aim signal equation will be much more simpler. We can write it as AC into 1 plus mu cos omega mt into cos omega ct. This is the equation for a single tone modulation. When the message is sinusoidal signal with only one frequency, this is how the aim signal equation looks like. We have written the general equation in previous slide. If the message is having single frequency, this is how we can write. And why did I write this? By looking at the shape of the message, I have understood that message is sinusoidal. It is a single frequency message, and that's why I've written this equation. Okay. Now, what is the peak amplitude of the message? Maximum peak amplitude of the message. AM signals peak amplitude changes with time. What is the maximum peak? If you want maximum peak, this should become 1, and if this becomes 1, whenever this becomes 1, we get peaks. Whenever this cos omega ct becomes 1, we get peaks. See this one? This is a peak. This is a peak. This is a peak. This is a peak. And whenever this becomes minus 1, whenever the cos omega ct takes minus 1, we get negative peaks. See this one? These are the negative peaks which we get when cos omega ct becomes minus 1. Right? We want maximum positive peak. Amax means we want maximum positive peak. Maximum positive peak. We are interested in maximum positive. We are having lot of positive peaks. Among them, we want the maximum positive. How much is the maximum positive peak? Maximum positive peak happens when this becomes maximum, when this part becomes maximum. This is deciding the peaks, and this decides the amplitude of that peak. And when this is maximum, we get the maximum peak. See this one? We get maximum peak when this part becomes maximum. In this part, the first part is constant, the second part is varying with time. So when the second part is maximum, we get the maximum positive peak. And what is the maximum value possible here? When cos becomes plus 1, we get maximum. And what is the maximum value possible here? It is AC into 1 plus mu. Maximum is possible when cos is plus 1, and we get positive peak when cos omega t is plus 1. So that is the maximum positive peak. A min. We are interested in minimum positive peak. Minimum positive peak. We want positive peak. Positive peak means when cos omega t becomes plus 1, that is when we get positive peak. We want only positive peaks, and we want minimum positive peak. So we get positive peak when cos omega ct is plus 1, and the amplitude of positive peak is decided by this part. When this part becomes minimum, we get minimum positive peak. And when will this part become minimum? When cos omega t takes the minimum value. And what is the minimum value of cos omega ct? The minimum value of cos omega t is minus 1. And we want positive peak, that's why it happens only when cos omega t becomes plus 1. Because we want minimum positive peak, when this becomes minimum, and this part becomes minimum, that is when we get minimum positive. So maximum positive peak is AC into 1 plus mu, and a minimum positive peak, this is AC into 1 minus mu. And what is the midpoint of these two? The midpoint of these two. What is the midpoint of these two? If you want midpoint, what should we do? Just average it. Just average it. If you add these two, this part gets cancelled, we get AC. The midpoint of maximum positive peak and minimum positive peak is the carry peak amplitude of the unmodulated carrier. So this is AC. AC is the midpoint of A max and A min. So this is A max and this is A min. Okay. Next, how to find mu value? So you can observe, if you know A max and A min, if you just average them, or if you find the midpoint of A max and A min, we get AC. Once you know AC, you know A max, you know AC, you can substitute these two values, you can find mu. That is how you can find it. Or you just take the ratio of these two, that is of the form a by b equal to c by d. Then if you do a minus b by a plus b equal to b minus d by b plus d, something like that, then you'll get the formula for mu. Or solve these two equations to get the formula for mu, and that formula will be mu equal to a max minus a min divided by, if you solve these two equations, you get a formula for mu, which is a max minus a min divided by a max plus a min. So this is the formula for modulation index using maximum peak amplitude and minimum peak amplitude. Okay, so using that, let's calculate the modulation index. I've done some derivation also here. I've revised the concept of envelope AM signal. Its envelope, its peak positive, maximum positive peak and minimum positive peak. So let's find the modulation index in this question. Let's actually solve the question now. So mu equal to a max. How much is a max? It is 150. A max is 150 minus a min is how much? A min is minimum positive peak is 30 here, divided by a max plus a min, which is 120 divided by 180. 120 divided by 180, which is 2 by 3 or 0.66. Option D is the right answer. Is that okay? Is it clear till this point? Can I move ahead? I'm moving on to the next question. Same data, but tricky question. The question asked is different with the same data. Let's move to the next one. Same data, same diagram, but I'm asking you a different question here. So a max is given, a min is given. From that AC we can calculate. AC is average of a max and a min, which we have calculated previously. A max plus a min divided by 2, which is 90. Peak amplitude of the unmodulated carrier is 90. Right. Now read through the question. The total power of modulated signal in watts and the amplitude of additional carrier which must be added to the waveform to attain a modulation index of 20% or 0.2 are respectively. They're asking two questions here. What is the modulation index? Earlier we have calculated for this one, a max minus a min divided by a max plus a min. It is 150 minus 30 by 150 plus 30. We have calculated that in the previous slide. We got it as 2 by 3 or 0.66. Or if you multiply with 100, we can say it as 66%. They're saying they want a modulation index of only 20%, it seems. Is that possible? By making some changes? Yes, it is possible. They're asking the amplitude of additional carrier which must be added to the waveform. They're saying that they will add an extra carrier to this signal. For this signal, they will add an extra carrier, it seems. When you add an extra carrier, what happens? Modulation index changes, right? So how much should be the amplitude of that extra carrier so that modulation index becomes from 0.66, it should become 0.2, it seems. That is the question. Okay, we will analyze the second part of the question. That is a little tricky. We will analyze it in the next slide. But first, let us calculate the easy part, the total power. The total power of modulated signal they are asking. This is the modulated signal. This one. This is the modulated signal. This is the envelope. Envelope is not the modulated signal. This is not the modulated signal. Okay. This is envelope of modulated signal. So this signal power they are asking. Okay. So we know AC. We know mu. If you know peak amplitude and if you know mu, can we calculate the total power of modulated signal? Can we calculate? PT, power requirement of AM signal, is equal to PC into 1 plus mu square by 2. And what is carrier power formula? It is AC square divided by 2R into 1 plus mu square divided by 2. Since resistance is not given in the question, resistance of antenna is not given in the question. Whenever resistance is not given, you can take it as 1. And AC value we know it is 90. 90 square divided by 2 into 1. Resistance is not given, so I have taken it as 1 into 1 plus. What is the mu value? Mu value for this one, for AM signal, before modifying it, before adding the carrier they're asking. So mu square is 4 by 9 divided by 2. Okay, right. So this is equal to, first part is 90 square by 2 plus second part is 90 square by 2 into 4 divided by 9 into 2. This is 4 by 9 into 2. 4, 2, 2 cancelled. In this 90 square, 1 9 gets cancelled. 90 square is 90 into 90. In that 90 into 90, 1 9 gets cancelled, it becomes 900. This part becomes 900. So the answer is 90 square by 2 is 8100 divided by 2, which is 4050. 90 square by 2 is 4050 plus 90 square by 9 is 900. So it becomes 4950. Because it is power, the unit is watts. So the answer is 4950 watts, but 3 options have the same thing. So solving the first one is not going to do any good for us. So we have to solve the second one. Anyway, we have answered one question here. When this diagram is given, we can calculate the power of modulated signal also. Right, when this diagram is given, from the data A max and A min, we can find AC and mu. From those two values, we can find the power. Okay, now let's move on to the next slide. So S of t AM, original signal given is AC into 1 plus, because we know it is sinusoidal, let us write the sinusoidal signal equation. Basically, we write as AC into 1 plus KAM of t into cos omega ct when we don't know the message. When we clearly know that the message is sinusoidal, you can write this equation because it's more easy to analyze. Now, let us write AC value. AC is 90, we know that, plus mu value is 0.5. Sorry, no, it's not 0.5. 2 by 3, right? It is 2 by 3. Is 2 by 3 cos omega mt into cos omega ct. So what did I write here? I have written the equation of whatever diagram is given in the previous slide. Whatever diagram is given here, this diagram, this is AM modulated signal, and that signal's equation I have written from the parameters that we know. We don't know some certain things. We don't know the frequency of the message. We don't know the frequency of the carrier. Apart from those things, whatever we know, we have written. Next, what are they doing now? The new AM signal. The new AM signal, let me call it as S of t AM dash. So how are they creating the new AM signal? They are adding the extra carrier, it seems. For this signal, they are adding a carrier. See this one, see, read the question. The amplitude of additional carrier which must be added to the waveform. For this waveform, they are adding additional carrier to attain a modulation index of 20%. Right. They are adding an additional carrier. So let me call it as AC dash into cos omega ct. This is the additional carrier that they are adding to change the modulation index. This is the additional carrier. And peak amplitude of additional carrier, I'm taking it as AC dash. So what are they asking us? The amplitude of the additional carrier. See, carrier means sinusoidal signal. For sinusoidal signal, we don't talk about amplitude, we talk about peak amplitude. Even if they say amplitude also, they are interested in peak amplitude, because sinusoidal signal amplitude will be always changing. The only amplitude in the sinusoidal signal that we will be interested in is the peak amplitude. So though they have not mentioned, you can understand that they are talking about peak amplitude. So the peak amplitude of additional carrier, which must be added to the waveform to attain a modulation index of 20%. So they are asking us to find this AC dash, this additional carrier's peak amplitude. What should be this value so that this total signal has a modulation index of 20% or 0.2? That is the question. Now let us analyze this. Okay. Right. Now let's understand this. So it is 90. So let me just rewrite this. 90 cos omega t plus AC dash. These two terms are having same term, cos omega ct term, plus 2 by 3 into 90 into cos omega mt into cos omega ct. See this one, I've just expanded this part and written this. Total 1, 2 and 3 terms. 3 terms I've written. See this one, these two are having same terms, cos omega c terms, so that's why I've taken, we can take common cos omega ct. So 90 plus ac dash into cos omega ct plus this term. Now let's take, now the total carrier amplitude is how much? The new peak amplitude of the carrier is not just 90 or ac dash. AC dash is the added carrier. It is the addition, whatever extra we have added. After adding this, what is the peak amplitude of the carrier? It's not 90 anymore, it's 90 plus AC dash. To get the general format of this equation, if you can arrange it, AM signal in this format, we can get the modulation index very easy. Whatever is the maximum amplitude possible in this part, if you take carrier completely common, in the sideband part, whatever is the maximum amplitude possible or maximum magnitude possible, that is the modulation index. See this one? Here, maximum magnitude possible is when cos happens to be 1, which is mu. Right? So 90 plus AC dash is the peak amplitude of the new AM signal. Because of adding this one, peak amplitude of the carrier should change, and that is 90 plus AC dash. And take cos omega ct also common, so that we are writing this equation in this format. So to write this equation in this format, new carrier amplitude is not just 90, it is 90 plus AC dash, which we have to take common. Now in this part it will be 1. That is what we want when we want to find modulation index, plus what is remaining in this part? Cos omega mt is remaining. Cos omega mt is remaining, and 2 by 3 into 90 is remaining. But 90 plus AC dash is not present here, so let's divide this by 90 plus AC dash. Is that okay? Now this is in standard form of AM signal equation. So what is the maximum amplitude possible here? That is what is modulation index. The new modulation index, let me call it as mu dash. So how much is that? It is 2 by 3 into 90 divided by 90 plus AC dash, which is equal to, so 3 30s, it is 60 divided by 90 plus AC dash. Okay, and how much is that value? Mu dash value is 0.2. This value should be 0.2. Since we know this value should be 0.2, if you substitute and solve this, you will get AC dash. Let's solve this. This 90 plus AC dash is equal to 60 divided by 0.2, or 60 divided by 0.2 is nothing but 60 into 5. 60 divided by 0.2, 1 by 0.2 is 5, which is 300, and AC dash should be equal to 300 minus 90 is 210. So which means you have to add a carrier with a peak amplitude of 210 volts, then only the modulation index will change to 0.2 or 20%. Okay, which means the peak amplitude of the carrier, new AM signal peak amplitude is 90 plus AC dash, which is 300 volts. Okay, I hope it is clear till this point. If there is any confusion after the session, just try to solve it in your own way with the same understanding. Try to do it, solve it on your own, then it will become more clear. If at all, if there is any confusion, we can remove the confusions only when we solve it on our own. Okay, right. Can you solve the next one? So try this one. Keep trying this one. I'll be back in a minute. My battery is dying, so I have to connect my charger. So give me 2 minutes, I'll be back. So in the meantime, you just solve this question. Finished? Anybody solved it? Wonderful question. Very good question. See, for practical messages, figuring out bandwidth is not so easy. Okay, so they have given a message where figuring out bandwidth is not so easy. So bandwidth definition is the range of positive frequencies, right? If you look at this one, it has infinite range. Infinite messages we can't transmit at all because if the bandwidth of message is infinity, bandwidth of modulated signal also will be infinity, which we can't transmit because we don't have infinite bandwidth. For any communication channel, we don't have infinite bandwidth. Right, so that's why we take some limited frequencies. We consider limited frequencies as bandwidth in a signal which has infinite frequencies. Though there are infinite frequencies, of them only few frequencies are significant. For other frequencies, the magnitude will be not significant. For example, I'll just plot this. You'll understand it better. It is not an easy diagram to plot, but rough shape is okay. Not exact shape. Exact shape is not required. So m of t Fourier transform, whenever we are discussing about Fourier transform or bandwidth, whenever you want to understand bandwidth, find the Fourier transform. So Fourier transform m of t is m of f, which is, it is in the form of a format of e power minus 80 into u of t. E power minus 80 into u of t. Fourier transform is e power minus 80 into u of t. Signal of this form, Fourier transform is 1 by a plus j omega. 1 by a plus j omega. Okay, so right, so 1 by a plus j omega, which is here in this case e power minus pi t into u of t, has a Fourier transform of 1 by 1 plus j pi, right? So this is m of f. This is what is m of f. So this, if you want to plot m of f, it is complex, so you have to plot the magnitude part and phase part separately. But when we are talking about bandwidth, we are interested only in the magnitude part. Since m of f is not real, since it is complex, plot only the magnitude. If it is real, you can plot the total part because its phase part will be anyway 0. Whenever the spectrum is complex or whenever the Fourier transform is complex, plot only the magnitude part when you are analyzing bandwidth, because bandwidth is decided by the magnitude spectrum. So how much is mod m of f? It is 1 divided by under root of 1 plus pi square. Magnitude of this is 1 by root of 1 plus pi square. So if you plot it, one second, j omega, my mistake, sorry. I've written a blunder here. E power minus 80 into u of t Fourier transform is 1 by a plus j omega. This is the Fourier transform. So in place of a, we are having pi. It is 1 by pi plus j omega. So the magnitude of this is 1 by root of omega square plus pi square. Root of pi square plus omega square, which is what I have written. So if you plot it at omega equal to 0, it is 1 by pi square. What is it? At omega equal to 0, it is 1 by root of pi square, which is 1 by pi. Correct? As omega increases, denominator increases, and hence the magnitude decreases. It is some kind of decreasing shape. It's not exactly exponential or something like that. It's some kind of decreasing shape. For negative frequency also, as omega increases negatively, then also because we are squaring, it is again decreasing. It's not exponential. It is some kind of decreasing shape. Okay. Now see this one. It is having infinite frequencies. No. What frequencies to consider as bandwidth? The range of positive frequencies in which the spectrum is significant. For what range it is significant? Significant means it is according to our definition. How much we treat it as significant is, it is our definition, right? So here what they are doing is, so that's why there is there are multiple bandwidth definitions that we have in our engineering. We have 3 dB bandwidth, 6 dB bandwidth. So there are a lot of bandwidth definitions defined for practical signals because they have, in general, many signals have infinite bandwidths. Okay, many signals. Practical signals will not have infinite bandwidth. Okay, so if you take some theoretical signals, they'll have infinite bandwidth. Practical signals like voice, audio, video, they have fixed bandwidth only. They don't have infinite bandwidth. But signals like this, some theoretical signals like this, they definitely have infinite bandwidth. So that is when we need some kind of bandwidth to restrict the bandwidth to be limited. Right. So 3 dB means 3 dB bandwidth means the bandwidth range of frequencies up to which the magnitude becomes 1 by root 2 times of the peak magnitude. 1 by pi is the peak magnitude, right? If you talk about 3 dB bandwidth, you are talking about some frequency. You are talking about range of frequencies. At that end, the magnitude should be 1 by root 2 times of this. Root 2 times less than this. So, but the definition here is different. The bandwidth that they are considering is different here. The maximum frequency present in this signal is decided up to the point. Maximum frequency is decided up to the point at which magnitude becomes 1/5 of the maximum value. What are they deciding as bandwidth? Bandwidth is decided up to the point at which magnitude becomes 1/5. 1/5 of the maximum value. What is maximum value? Maximum amplitude is 1 by pi. 1/5 is 1 by pi by 5 is 1 by 5 pi. 1 by 5 pi. That is the maximum. That is the amplitude at this frequency, which is considered as bandwidth. So this they are considering as bandwidth. Let's say this is B. Is that okay? Whatever we take as bandwidth, I'm taking the representation for this point as B because this range we are calling it as bandwidth. If you want, you can take some other notation, no problem. Now, if a single sideband suppressed carrier is used as modulation scheme with a carrier frequency of 200 megahertz, then the bandwidth of modulated signal is, see, they are talking about bandwidth of Ssbsc modulated signal. See, this is the message. Finally, what they are doing is they are doing Ssbsc modulation. Ssbsc modulation. In what is the bandwidth of Ssbsc modulation? In Ssbsc modulation, we send only one sideband, which means only this part will send. The bandwidth of this part is B. So after doing Ssbsc modulation, also it is same as message bandwidth. Ssbsc modulated signal bandwidth after modulation is same as bandwidth of message. Original message which we are using for modulation. For DSBSC or DSBFC, bandwidth of DSBSC or DSBFC is 2 times bandwidth of message. Okay, so if you can find the bandwidth of the message, it is as good as finding the bandwidth of Ssbsc modulated signal. They're asking us that only. Then the bandwidth of modulated signal or Ssbsc modulated signal. So they're effectively asking us to find the bandwidth of this one. For this one, figuring out bandwidth is not so easy. So they have given us a hint how to take the bandwidth. They are saying that this range where the magnitude becomes 1/5, that range they are considering as bandwidth. So this answer is what they're asking us. So it's a simple question. Once you have understood the question, solving it is not so difficult. So mod m of f at f equal to b, because bandwidth you can deal in terms of f or omega, both are fine. Let me deal in terms of f because I'm comfortable with f. At f equal to b, what is it? What is the magnitude at f equal to b? So let us substitute in place of f b, root of omega square is 2 pi b whole square, 2 pi f in place of f, 2 pi f. This is omega is 2 pi f. In place of f, we have to substitute b, not in place of omega. 2 pi b whole square plus pi square. Okay, but what is this magnitude at f equal to b? At f equal to b, what is the magnitude? It is 1 by 5 pi. 1 by 5 pi is the magnitude. Okay, so 1 divided by 2 pi b square plus pi square. There is a root here. So if you square both sides, then this root will go. It will become like this. Correct? So now let us solve this one. 1 by 25 pi square is equal to 1 divided by 4 pi square b square plus pi square. This implies if you remove the numerators, only if you can equate the denominators, 25 pi square equal to 4 pi square b square plus pi square. So this pi square onto the other side, it becomes 24 pi square. I'm equating the denominators. Then this pi square onto the other side becomes 24 pi square is equal to 4 pi square into b square. Pi square gets cancelled, pi square gets cancelled, 4 gets cancelled with this, it becomes 6. So b square is 6 and b is equal to root 6. Correct? Wonderful. Looks like a tricky question, but once you understand the question correctly, then solving it is not a big deal. Okay, I hope it is clear till this point. I'm moving ahead to the next question. How about this one? Try this one. Message signal is given. Equation of modulated wave for amplitude modulation with 50% modulation is S of t is equal to AC into this is not sinusoidal message, so it's a general message. Let's write general equation. The general equation for a modulated signal is AC into 1 plus Ka into m of t into cos omega ct. This is the general equation. And what is given about message? What is given about message? It is 1 plus Ka into m of t is 1 by 1 plus t square. I'm substituting the message equation here into cos omega ct. Okay. So what do we want here? The equation of modulated wave for amplitude modulation with 50% modulation. So they have given us the mu value also. Mu is given as 0.5. Okay. So what is mu here? Because there is a one unknown here. Ka is the unknown here. So modulation index, how do we find it? When you take the carrier completely common, then we have a 1 here. And in the remaining part, which is the sideband part, the message part, in this part, whatever is the maximum magnitude, mu is nothing but the maximum magnitude possible in this part. The modulus of Ka divided by 1 plus t square modulus maximum. Or we know we have written as Ka modulus of m of t maximum. That is the mu value. That is how we find the mu value. Ka mod m of t maximum. And it is given that mu value is 0.5. It is given that mu value is 0.5. Right? So tell me this. Ka divided by 1 plus t square maximum. When is it going to become maximum? Can anyone tell me? When will this become maximum? This part becomes maximum because t is in the variable is in the denominator. Because the variable is in the denominator, as t increases, the overall value decreases. Okay. When you put t equal to 0, that is when we get the maximum value. When t equal to 0, we get maximum. As t increases positively or t increases negatively, both ways, the denominator increases and the overall value decreases. So maximum happens at t equal to 0. So the maximum happens at t equal to 0, which is Ka by 1 plus 0. So the maximum value possible for this is Ka by 1 plus 0, which means Ka value is 0.5. So Ka is 0.5. Let us substitute it in this equation. So we get the answer as option B. Okay. We don't need to solve it like this. Just by looking at the options also we can figure it out. Because message is 1 by 1 plus t square, we can observe that okay, all three options have the same thing, 1 by 1 plus t square. So we want mu of 0.5. Mu means what? The maximum magnitude possible in this part. The maximum magnitude possible in this part should be 0.5. So you can observe from this equation with the common sense we can figure out that what is when is it maximum? When t equal to 0 it becomes maximum. If you put t equal to 0, we get a 1 here. So this is the equation when modulation index is 1, and you can, if this is maximum and t equal to 0, put t equal to 0, we get 0.5. So this is the equation when modulation index is 0.5. Similarly, third one, if you put t equal to 0, we get the maximum value here. So this is the equation when modulation index is 2. So we want a modulation index of 0.5. So that's why the answer is option B. We don't need to solve it like this. We can directly guess the answer just by looking at the options also. right? So I'm moving on to the next one. Next question. The signal m of t, whose ft means Fourier transform, m of f is shown in the figure. Fourier transform is shown in the figure. Surajit, the maximum value of any arbitrary signal. You mean maximum value means maximum amplitude only, right? Maximum amplitude has to be found from time domain only, no? Because, are you talking about this question only, right? I think you're talking about this question only. Okay, I think you are talking about the previous one. Yeah. See here, in the time domain equation only, we have discussed that modulation index is Ka times mod m of t max. M of t is time domain signal. So for time domain signal only, we have to find the maximum magnitude, not for the frequency domain one, which is m of f. We are not interested in m of f at all here. When you are calculating mu, we are not interested in m of f. We are interested in peak amplitude of message in time domain. Okay. If there is any further question, you can let me know. Right. So message Fourier transform is given. Message in time domain is not given here. Message in frequency domain is given. So m of f is shown in the figure, is to be transmitted from one point to another. It is given that m of t, which means the inverse Fourier transform of this one, is taking amplitudes from -3 to +3 it seems. Which means they have given some m of t. I don't know what is the shape because they have not given it. Whatever might be the shape, it is having a peak of 3 and negative peak of -3 it seems. It need not have a symmetrical shape also. It is having a peak amplitude of 3, negative peak of -3, but its shape need not be sinusoidal. It can be any shape. It can be any shape. That is what they have given in this question. Message takes an amplitude from -3 to +3. Shape can be anything. Right. If an FM system is employed, which means frequency modulation they are using for this message. To transmit this message, they are using frequency modulation. So FM system is employed for transmission, and frequency sensitivity is given as 60 kilohertz per volt. Then the bandwidth of modulated signal is, okay, right? Bandwidth of AM modulated signal. So bandwidth of modulated signal. Here it is FM modulated signal because we are using FM system. So the formula for FM modulated signal bandwidth is 2 into beta plus 1 into FM is one formula. Beta plus 1 into FM. FM means message frequency or message bandwidth. Or 2 into del f plus bandwidth of message. Del f is the frequency deviation. FM is message frequency. FM we write it because when we deal with single tone modulation, FM is the frequency in the message. That's why we use this formula. But for a general message, we can take this FM as the highest frequency in the message or bandwidth of message. So beta is modulation index. Modulation index is not given here. So we can take, let's do the second formula. Let's use the second one. 2 into del f plus FM. How do we find del f? Message frequency. What is the highest frequency in the message? FM or bandwidth of the message. We can take the notation as B or FM. Bandwidth of the message is 20 kilohertz. Okay. Next. Frequency deviation. How do we find frequency deviation? Frequency deviation, there are two formulas for it. Kf into AM is one formula, or Kf into mod m of t maximum. Kf into AM is a formula which is valid for single tone case, but here message is not given as single tone or sinusoidal message. So Kf into mod m of t maximum, that is the general formula for frequency deviation. So Kf is given as 60 kilo, and it is the information given about messages takes voltages from -3 to +3 it seems. So maximum magnitude of the message is 3. So it is 180 kilohertz. Then there is another formula for the frequency deviation which is beta times FM, but beta is not given in the question. So that's why we have to use kf mod m of t maximum, because the information is given to substitute for these parameters. So 180 kilohertz is the frequency deviation. You can substitute here 2 times frequency deviation is 180 kilohertz plus frequency, highest frequency in the message or bandwidth of the message is 20 kilohertz. From this diagram we can understand that from this whole diagram the only information that is important for us is the bandwidth of the message or highest frequency in a message, which is 20 kilohertz. 180 plus 20 is 200. 200 into 2 is 400. 400 kilohertz. That is the answer. Okay. So I believe it is clear to this point. So moving on to the next question. Right. So a message signal 5 sync 400t. Message is not sinusoidal, message is sync function. Message is sync function. M of t is 5 sync of 400t. Right. I'll revise some basic here. Let me revise some basic here quickly. Sin at by pi t. This is one Fourier transform that you have to remember. This is sync function only in one format. Fourier transform is a rectangle of omega divided by 2a. Okay, so if you plot it, Fourier transform sin at by pi t is it's a rectangle with a height of 1 unit from minus a to plus a as a function of omega. This is very important, as a function of omega. If you want to write it as a function of f, it is a by 2 pi minus a by 2 pi here. Now if you want, you can rewrite this as I'll divide and multiply with a, so then it will become sin at by 80. See this one, a I'm multiplying and dividing, and pi I'm putting it outside, so that I can write it as a by pi into sampling of 80, right? Or you can also write it as a by pi into sync of 80 by pi. Sync of 80 by pi. Those Fourier transforms, same thing. I did not change any constants here. I have multiplied and divided with a, so no change on the other side. So Fourier transform will be rectangle of omega by a, omega by 2a. Now if you send this a by pi onto the other side, it is pi by a into rectangle of omega by 2. Okay. Okay. So which means we can find the exact Fourier transform sync of 80 also. So I'm multiplying t with pi. So then what happens in frequency domain? You have to divide omega with pi. I'm talking about scaling property of Fourier transform. T, if you multiply with pi, omega should be divided with pi. So it becomes 2 pi a. When you multiply t with pi, on the other side it becomes 1 by pi extra, it should become 1 by a. So we can find the exact Fourier transform sync of 80 also, but it's not worth remembering. So remember only this. From this we can find whatever we want. Okay, from this we can find whatever we want. So how to do it? See this one? So convert this into that format. Whatever Fourier transform we remember, convert this into that format. 5 sync of 400 means, can we write as sin 400 pi t. Sync of 80 is sin 8 pi 80 divided by pi 80. Sync means there should be an extra pi, sin pi 400t by pi 400. I'm just converting this into a format for which I remember the Fourier transform. So what is the Fourier transform for this? 5 by 400 you put it aside. 5 by 400 you put it aside. The remaining part is in the format of sin 80 by pi t, sin 400 pi t divided by pi t. So in the place of a we are having 400. It is rectangle of omega divided by 2a. In place of a, we're having 400 pi, which is 800. So I'm writing the Fourier transform of the given message because it might be important for me. That's why. Right. So frequency modulates the carrier 50 cos 2 pi fct. The modulation index is 6 seconds. The maximum frequency deviation of the modulated signal. They're asking us to find maximum frequency deviation del f and the power in the modulated signal. Power in the modulated signal. Power in the modulated signal is very easy because for FM signal, power in the modulated signal is same as carrier power, which is AC square divided by 2R. Resistance is not mentioned in the question, so we can take it as 1. So AC is given as 50 square divided by 2. So R is not given, so let us take it as 1. So 50 square is 2500 divided by 2 is 1250. So it is 1.25 kilowatt. 1.25 kilowatt. There are 3 options with the same answer. So we are not able to rule out, get our option using only the power answer. So we have to solve for the first part also. The maximum frequency deviation of the modulated signal. Maximum frequency deviation of modulated signal del f is equal to kf into am is one formula. Kf into mod m of t maximum is one thing. But kf is not given in the question. Kf is not given. So that's why let's use the other one. It is beta times fm. Fm is maximum frequency in the message. Fm is maximum frequency for sinusoidal message. It is the only frequency present. For general message, Fm is the highest frequency. So beta is 6. Fm is the highest frequency in the message. What is the highest frequency in the message? Let me plot this. When you are talking about bandwidth, the height of the rectangle is not important for us. Rectangle of omega by 800 minus 400 pi 2 plus 400 pi as a function of omega. The height is 5 by 400 or 1 by 80. What is the highest frequency? 400 pi radians per second. Bandwidth of this message. Bandwidth of the message is 400 pi radians per second or 200 hertz. 400 pi radians per second is correct, which is same as 200 hertz. So bandwidth of the message is 200. Whenever we use in the formulas FM, which means frequency of the message. For sinusoidal signals, we have written this formula. We have taken the notation as FM. But for other messages, you can take the highest frequency and substitute in place of FM. Or bandwidth of the message, you have to substitute in this place, which is 1200 hertz or 1.2 kilohertz. So frequency deviation is 1.2 kilohertz and power is 1.25 kilohertz. Answer is option C. Okay. Right, I'm moving on to the next question. Find the maximum and minimum instantaneous frequencies of FM modulated signal. So given data is frequency sensitivity of FM signal is given as 50 kilohertz per volt. Carrier frequency is given 5 megahertz. They're asking us to find instantaneous frequency maximum value and instantaneous frequency minimum value. Okay, let me recollect some basics here. In instant frequency formula, instant frequency is given as fc plus kf into m of t, as simple as that. So if you want instantaneous frequency to be maximum, then it happens only when m of t is maximum, because fc is a constant, kf is a constant. The change is happening only because of m of t. When m of t is maximum, that is when we get maximum instantaneous frequency, and we get minimum instantaneous frequency when m of t is minimum. So there should be a minus sign. No, you might ask me. See, when I say minimum m of t, in that itself there might be the negative sign. Okay, if a minimum value of m of t is minus 4, that minus 4 we are going to substitute here, then you will get a negative sign. Okay, very good. Now what is given? Fc is 5 megahertz FC is 5 mega plus KF. K is 50 kilohertz, 50 kilo, 5 mega plus KF is 50 kilo. Now let us substitute the maximum and minimum amplitudes of message. What is the maximum amplitude of message? M of t maximum is 10, M of t minimum is minus 10. This is 10 and this is minus 10. So this is equal to 50 megahertz plus 500 kilohertz. This is 5.5 megahertz. And this is 5 megahertz plus minus 500 kilohertz is minus, this is 5 megahertz minus 500 kilohertz is 4.5 megahertz. So we know maximum instantaneous frequency and minimum instantaneous frequency now. So it is 5.5 and 4.5. Answer is option A. Very good, Surajit. I hope it is clear till this point. Next one. Similar question. Message signal is same, but the other information is different. Message signal is given in this here, given here. M of t is given here. The peak frequency deviation of the above FM signal is, for this signal, what is the peak frequency deviation? When you want peak frequency deviation, right? Okay, let's go back with the basics. Let me recollect the basics here. How to find frequency deviation in any given problem. If the problem is tricky, if you're not able to observe it directly, then how to do it. FM signal, modulated signal equation is AC cos of omega ct plus 2 pi kf integration of m of t dt. Okay, right. Now the angle here is theta of t is, the angle of the signal is omega ct plus 2 pi kf integration of m of t dt. So this is the angle, and if you want to find instantaneous frequency, then you can find it using the angle, using the general relation of sinusoidal signals. If you know angle of sinusoidal signal, and if you want to find instantaneous frequency of the signal, this is the relation you can use for any sinusoidal signal. So let us apply. It is 1 by 2 pi. Differentiation of this with respect to t is omega c is the differentiation of this part plus 2 pi kf. Differentiation of this part is just m of t, which is equal to omega c divided by 2 pi is fc plus 2 by 2 pi gets cancelled, kf into m of t. We know this already. Fi equal to fc plus kf into m of t. How do we get this? Whenever any angle is given, just differentiate the angle and divide with 2 pi, you will get the instantaneous frequency. When you get the instantaneous frequency, this is the base frequency, and the deviation is because of this. The deviation is because of the message part. So maximum frequency deviation, you can take it as del f or del f max. Maximum frequency deviation is decided by this part. Whatever is the maximum magnitude of the signal, maximum magnitude of this part which is responsible for deviation, the part that is responsible for deviation, in that part, whatever is the maximum magnitude possible, that will decide the maximum frequency deviation. Okay, any confusions, you have to follow this procedure. This is the general one. Okay. So peak frequency deviation or maximum frequency deviation, it is the same thing. So from this, let us write the angle. Angle is 2 pi fct plus 100 into integration of m of lambda into d lambda. So let's differentiate with theta of t, differentiate with time, then becomes 2 pi fc plus 100 into m of lambda. So now Fi, instantaneous frequency, is equal to 1 by 2 pi d by dt of theta of t is equal to fc plus 100 divided by 2 pi into m of lambda, or m of t you can write, because it's a function of time. Inside integration it can be any variable, but yeah. Now look at this one. So deviation is because of this part, and maximum frequency deviation is equal to the maximum magnitude possible in this part. What is the maximum magnitude possible in this part? Maximum magnitude possible in this part is when m of t become, whatever is the maximum magnitude of m of t, that will decide it. So maximum magnitude of m of t is, amplitudes possible for m of t are 10 is the highest amplitude and -5 is the lowest. If we take the magnitude of this, modulus of this, the highest possible is 10. So 100 divided by 2 pi into 10, which is equal to 1000 divided by 2 pi, or 500 divided by pi, which is option B. Or the other way is, you could have compared also, right? See this one? You can compare this equation with this equation, but not every time it will be so straightforward. Okay, that's why I've told you the general procedure here. This procedure you can apply for any equation, for any this angle if you take, and if you differentiate you'll get frequency. That is applicable for phase modulated signals also. This basic you can apply for all frequency modulation as well as phase modulated signals. Right. For this question particularly, if you look at the general equation, AC into cos of omega ct plus 2 pi kf integration of m of t dt. If you compare with this, you can observe that 2 pi kf is 100. In this question it is possible, but if it is more complicated, then simple comparisons will not help. Okay, so kf is 100 divided by 2 pi, and they are asking us to find peak frequency deviation. Frequency deviation formula is given as kf into mod m of t maximum. That is the general formula which is valid for all messages. So kf we have found by comparison as 100 by 2 pi, and maximum amplitude of message is 10. Same answer you are getting. This is the easiest way. For this question, it is possible to just compare and get the answer quickly. But if the question is little tough or complicated or confusing, then just go with the basics. If you know angle, you can find instantaneous frequency. Once you know instantaneous frequency, you can find the maximum deviation of frequency. Okay. Right. I'm moving on to the next one. So in this question, they're talking about peak phase and frequency deviation. So what is the angle here? Now the basics that we have discussed previously will help us. So angle is 10 to the power of 8 pi t plus 3 sine 10 to the power of t. This is the angle. Okay, this is a simple sinusoidal signal, single tone modulation, right? So you don't need to take any general equations are not required here. Simple basics are sufficient. S of t, FM signal equation is equal to, they did not say if it is FM or not, but if it is FM or PM, when they don't mention, the same formulas are applicable there. It is 10 into cos of 10 to the power of 8 pi t plus 3 sine 10 power 3 t. So peak phase deviation, del phi, it is same as beta. Beta is the maximum magnitude possible in the phase part. In the phase part, what is the maximum magnitude possible? It is 3 units. When sine becomes +1, you get 3 as the maximum magnitude possible in the phase part. Maximum magnitude possible in the phase part will be the modulation index or maximum phase deviation. This is valid for both the FM signal as well as PM signal. Next, maximum frequency deviation is equal to beta times FM. In this case, beta is 3 and message frequency is 10 to the power of 3, 10 power 3 divided by 2. Ten power 3 divided by 2. Is that okay? Sorry, it is sine of 2 pi. My mistake here. Small mistake here. sine 2 pi 10 power 3. So message part is sine 2 pi 10 power 3t. So message frequency is 10 power 3. You can substitute in place of FM 10 power 3. It is 3 kilohertz. So peak phase deviation is 3 radians. Unit of phase deviation or beta, modulation index beta, is radians. So 3 radians is the phase deviation and 3 kilohertz is the frequency deviation. So option A is the correct answer. So option B also has similar data, but the order, you can take the order. The best option possible is option A, because first they're asking the peak phase deviation and then frequency deviation. According to the order, option A is correct. Option B also has same answers, but it's in the reverse order. Right? So let's move on to the next one. Try this one. Let m of t be a periodic triangle wave with 10 power minus 3 seconds as time period, maybe. Okay. As time period. 10 power minus 3 seconds might be the time period. Then I missed that word. With the maximum amplitude as minimum amplitude and maximum amplitude are 1 and minus 1. It seems. Minus m of t min is 1 means m of t minimum is minus 1. Maximum and minimum values of instantaneous frequency for a phase modulated wave with Kp, phase sensitivity is given. Okay, so given waveform, we don't need to draw actually. In this case, it's not required. Is it required? For instantaneous frequency, yes, actually it's not required. But anyway, let's draw it. Something like this. That's what it repeats. Maximum height is 1, minimum is minus 1. This is how m of t looks like. So Kp is given. So S of t is equal to AC into cos of omega Ct plus Kp into m of t. This is the equation for phase modulated signal. Okay. This is the equation for phase modulated signal. And for a phase modulated signal, phase deviation is very easy to find. Phase deviation is very easy to find. It is also same as modulation index, and that is given by the maximum magnitude in the phase part. Always the maximum magnitude in the phase part of modulated signal equation will give us phase deviation, maximum phase deviation. Is Kp mod m of t max, but that is not asked in the question. That is not what is asked in the question. The question is different. They're asking us about maximum and minimum instantaneous frequency. So let us figure out the instantaneous frequency here. To figure out instantaneous frequency, let me write here. The angle of an FM or PM modulated signal is omega Ct plus Kp into m of t is the angle. So just compare with this one. This is the equation of PM signal. In this PM signal equation, I have copied the angle part. This is how the angle looks like. So instantaneous frequency relation we know. If you know angle, from that you can find instantaneous frequency. I have discussed that in the previous slide also. Let's find this. If you differentiate this, it will be omega c. If you divide with 2 pi, it is fc plus kp divided by 2 pi into differentiation applied to m of t. It becomes d by dt of. So if you want fi maximum, see this one, I'm revising the concept here. If you want maximum instantaneous frequency, that happens when d by dt of m of t is max. Whatever is the maximum magnitude of message. Minimum instantaneous frequency. Minimum instantaneous frequency happens when d by dt of m of t is minimum. Okay. Right. Now, one more thing that can be asked is frequency deviation, maximum frequency deviation. Frequency deviation is, this is constant, and this is the base frequency, and frequency deviation is happening because of this term, and maximum deviation happens, whatever part is responsible for frequency deviation, in that part, whatever is the maximum magnitude possible, that itself is the maximum frequency deviation. This is the phase part. This is the phase part, and this is the part responsible for phase deviation. And whatever is the maximum magnitude of this part, that we can call it as maximum phase deviation. So maximum magnitude of the part responsible for frequency deviation, we can call it as maximum phase deviation. The term that is responsible for frequency deviation. In that term, find the maximum magnitude. Maximum magnitude. Okay, these are the three things that we can figure out from the angle equation, right? So we want differentiation of message, which means the slope of the message, right? We want the slope of the message, maximum slope of the message and minimum slope of the message. So let's go back. So FC is given or not? FC is given, right? 100 kilohertz. Let's substitute that here first. 100 kilohertz plus kp is given. What is kp given as? 2 pi. Let's substitute that also. Kp is 2 pi divided by 2 pi. Kp divided by 2 pi, I'm substituting here, multiplied with maximum slope and minimum slope. Maximum slope of message and minimum slope of the message. That will let us figure it out. So with 10 power minus 3 seconds as the time period, let me say this is 10 power minus 3. Let me say this point is 10 power minus 3. So that is not clearly given in the question. Some part of the question that I've given, the TTP guy has missed it. But anyway, let me take this as 10 power minus 3. So then what will be this value? This total thing is 4 times of this part. So this is 10 power minus 3 divided by 4. Okay. So this length is 10 power minus 3 divided by 4. If you assume time period is 10 power minus 3. We assume time period is 10 power minus 3 seconds. Now could you tell me, what is the slope here? That is what we want to figure out, right? So what do we want? We want the maximum slope and minimum slope. There is only 2 slopes. This is positive slope and this is negative slope. This will be the maximum slope and this will be the minimum slope. How much is the slope here? Can you tell me? It has increased by 1 unit in 10 power minus 3 by 4 seconds. In 1 second, how much it will increase? Or if you think of it as right angle triangle, tan theta. What is tan theta? Height divided by width. The slope here is 1 divided by 10 power minus 3 divided by 4, which is equal to 4 divided by 10 power minus 3 or 4 kilo. Correct? 10 power minus 3 into the numerator, it becomes kilo. 4 into the numerator, it becomes 4 kilo. And how about the opposite one? Since they both have same equal and opposite slopes, it will be minus 4 kilo. Correct? Minus 4,000. Many people say that the slope here is 1. No, it's not 1, because at 1 second the height is not 1. At 10 power minus 3 by 4 seconds it is 1. The time period is also very important here. Is it okay? Slope here, the positive slope is 4,000, my negative slope is minus 4,000. Here also positive plus 4,000, minus 4,000. Highest slope in the signal is 4,000 and lowest slope in the signal is minus 4,000. So let us substitute that. 4 kilo and 4 kilo. So this is 104 kilo and this is minus 4 kilo, right? Minimum slope is minus 4 kilo. This is 96 kilo. Yes, answer is option D. Is that okay? I believe it is clear till this point. So I've covered some wonderful questions based on frequency modulation as well and amplitude modulation as well. So let me cover one more model of question here. Yes, this model. So bandwidth of this modulated signal. So these questions are slightly confusing. So I'll tell you, see this one? In FM signal or PM signal, in FM or PM, in any angle modulated signal, which means FM or PM signal, so same basics are applicable. When 2 sinusoidal terms are there, with the different frequencies, or when two cos terms are there or sine terms are there with different frequencies, how to solve it? That is the question. Okay, so here I'm covering all models of questions here. In similar model, I'm covering different types possible there, different types that can be asked. AC cos of omega ct plus beta 1 cos omega 1t plus beta 2 sin omega 1t. See this one? Here it is same frequency, but cos and sine. Cos and sine, the angle inside cos and angle inside sine is same. In this, under this condition, beta value for this one, beta value is root of beta 1 square plus beta 2. See this one? Because this total thing can be written as root of beta 1 square plus beta 2 square into cos of omega 1t plus some angle phi. This total thing can be written in this form because the frequency is same. That's why we can write it in this form. I hope you're following. This is an easy model of easy question that can be asked. When the two sinusoidal terms present or in the message, there are two sinusoidal terms with the same frequency. In that case only the modulation index is very easy to find in this manner. And the next model possible is S of t is equal to AC cos of maximum phase deviation or modulation index. How do you find it? The maximum magnitude possible in the phase part. And how do you find frequency deviation? If you want to find frequency deviation, maximum frequency deviation, find the instantaneous frequency. And in the instantaneous frequency, there are two terms. One is constant part and the other part is varying part. The other part, varying part, is responsible for deviation. In that part, find the maximum magnitude. See this one? See, if it is cos omega 1t only, then you can add this 2 and you can write as beta 1 plus beta 2 into cos omega 1t. But that is not a question that can be asked, okay? Because they won't give us same frequencies with two terms, right? Because you can anyway add them. So what if the frequencies are different but both are constants? And one more model is possible. These are the three models that are possible. So I'll tell you some general idea to solve these questions. Okay. Right. Both cos terms or both sine terms with the different frequencies, not same frequencies. That is not a question at all. Different frequencies. How to solve it? So in this case, what is the maximum magnitude of two cos terms together? Maximum magnitude of two cos terms together. Is it possible to figure out? Yes, it is possible to figure out. No? When t becomes 0, when t is 0, cos becomes plus 1 and this cos also becomes plus 1, and we get back maximum at both places. That is the maximum possible value in this part. Correct? Maximum magnitude possible in the phase part. That is the phase deviation, maximum phase deviation, or beta. Beta or del f. Beta or del phi. Both are same. In this case, it is easy to figure out the phase part. The phase part maximum magnitude is easy to figure out because when two cos values are there, when two cos signals are added, the addition of these two will become maximum at t equal to 0. Correct or not? Imagine any two cos signals with same frequency, with the different frequencies. Definitely they will be having maximum magnitude at t equal to times 0. At 0 time both have maximum magnitude. When you add them, the resultant signal also has maximum magnitude at t equal to 0. So it's easy to figure out the maximum magnitude of two causes combined. Two causes combined, it's easy to figure out the maximum magnitude. So the maximum magnitude happens when t equal to 0. So if you put t equal to 0, it is beta 1 plus beta 2. It's very easy. Okay. Whereas here, beta or del phi, it's not easy to figure out. Because two sine terms, when is it maximum? At t equal to 0, definitely they are not maximum. At t equal to 0, it becomes 0. This also becomes 0. At some other point, they become maximum. And that point, it's not easy to figure out for two sine terms combined. Okay. So here, one parameter is easy to find. And here another parameter will be easy to find. Right. So here, let's figure out the other term, frequency deviation. If you want to figure out frequency deviation, what should be there? You should know instantaneous frequency. Right. Let's figure out the instantaneous frequency. Instantaneous frequency Fi is equal to. So differentiate this and divide with 2 pi. So this part becomes Fc plus. So if you differentiate this, it becomes cos becomes sine beta 1 sine omega 1t into omega 1 divided by 2 pi is beta 1 f1. I'm doing the differentiation directly, okay? I try to understand it so that space can be saved and you can understand it things easily. Cos differentiation is minus sine, so it becomes beta 1 into omega 1 outside. But when you're finding instantaneous frequency, the formula is 1 by 2 pi differentiation of angle. So you have to divide with 2 pi. Omega 1 divided by 2 pi is f1, beta 1 f1 minus beta 2 f2 into sine omega 2. We got the instantaneous frequency here. Here also, let us find the instantaneous frequency. Let us find the instantaneous frequency here. It is 1 by 2 pi into differentiation of this total angle. Fc plus differentiation of sine is cos. The beta 1 f1 sine cos omega 1t plus beta 2 f2 cos omega 2. So when two cos terms are there, it's easy to figure out the maximum magnitude. So this is the term responsible for frequency deviation. It is easy to figure out the frequency deviation when two sine terms are there in the phase. So maximum frequency deviation is the maximum magnitude of this part. Maximum magnitude of beta 1 f1 cos omega 1t plus beta 2 f2 cos omega 2. Modulus maximum. Can we figure out the maximum magnitude? Yes, it is easy to figure out when two constants are there. If you put t equal to 0, we get 1 and 1 here. So when you add them also, you'll get the maximum. So and how much is that? The maximum magnitude of this part happens when t equal to 0, which is beta 1 f1 plus beta 2 f2. I hope it is clear. So frequency deviation is easy to figure out. Next, here how about the frequency deviation? It's difficult to figure out the frequency deviation here, because when two sine terms are there, it's difficult to figure out, but this is how instantaneous frequency we get. But when you know modulation index, beta, we can figure out the frequency deviation as beta times fm. That formula is there, no? That only you can use, beta times fm. In this case, beta is what? Beta 1 plus beta 2 times fm. Fm is what? Since if you are talking about singleton case, fm is the only frequency present. But here there are two frequencies present in the message. There are two frequencies, f1 and f2. Whatever is the highest frequency, substitute that. Let me assume f2 is highest. F2 is highest. Let me substitute beta times fm. That simple formula you can use. In place of fm, substitute the highest frequency in the message. Because the frequency deviation, you can't get it from this. Okay. Whatever is easy, only one parameter will be easy here. Only one parameter will be easy to find in any combination, both causes or both signs. In any combination, only one parameter will be easy to find. In this combination, both causes are there. Wherever both cos terms are there, it is easy to figure out that term. Both causes are there in phase term, so that's why phase deviation is easy to figure out. So sine term, two sine terms in phase part, so which means if you differentiate two cos terms in frequency part. So since two constants are there in frequency part, it is easy to figure out the frequency deviation. Okay. So if you know frequency deviation, how to find the modulation index? Modulation index formula, if you remember, singleton case, del f divided by fm. You can use the same thing. Del f is beta 1 f1 plus beta 2 f2 divided by fm. In place of fm, there are two frequencies here. Substitute the highest frequency. Whenever there are multiple frequencies, take the highest frequency. Is that okay? This is how we solve the question. You don't need to by heart the formulas that we have derived. You can apply the basics that I have done here. So after the session, you can just recollect things by writing these things on your own. You'll get more clarity. Let's say this one, both sine terms. It's difficult to figure out the maximum. Both sine terms in phase part. In phase part, both sine terms means it's difficult to figure out the phase deviation, but it is easy to figure out the frequency deviation. How to figure out? I'll go with the general procedure. I will not use any formula. Okay, angle below. So how to find the instantaneous frequency? Divide this total thing by 2 pi and differentiate it. So it becomes fc plus 10 into fc minus sine differentiation is cos. So 400 pi divided by 2 pi is 200 into cos 400 pi t plus 5 into 200 pi outside when you differentiate, and this we are dividing with 2 pi, so it will be 100. So I'm applying the total formula 1 by 2 pi d by dt of theta of t. This is theta of t. I'm differentiating and dividing with 2 pi. I'm writing things directly so that we can save time. Same basics that we have done in the previous slide. So this is fc plus this is 2000 cos 4000 t 400 by t plus 500 cos 200 by t. Two cost terms, so it's easy to figure out the maximum frequency deviation. How much is the maximum frequency deviation? Maximum magnitude possible in the phase part, sorry, maximum magnitude possible in the deviation part, frequency deviation part. This is constant term, this is the term responsible for deviation. What is the maximum magnitude possible here? Maximum magnitude happens when t equal to 0. Put t equal to 0 and get the maximum magnitude, which is 2500 hertz is the unit of frequency. So they're asking us the bandwidth. Bandwidth is equal to 2 into del f plus fm. So 2 into del f is 2.5 kilohertz plus what is the highest frequency in the message? Highest frequency, there are two frequencies in the message, 100 hertz and 200 hertz. 200 hertz is the frequency, highest frequency. You can substitute that, which is 0.2 kilohertz. Yeah, 2.5 plus 0.2 is 2.7 kilohertz into 2 is 5.4 kilohertz. 5.4 kilohertz. Yeah, that is the answer. I think there is some typo error here. That is 4.5, 5.4, 6. Answer should be option C. There is typing mistake here, or if there is a typing mistake here, 0 and 0, 4000, 2000 if you take, then it will match with options, which is 54. Is that okay? Right, next one, two cost terms. If the two cost terms are there in the phase part, it's easy to figure out the maximum phase deviation. And how much is that? When you put t equal to 0, we get maximum. If you put t equal to 0, what is the maximum magnitude possible in the phase part? It is 8 plus 6, which is 14. Right? That is the maximum phase deviation, which is same as modulation index. Is that okay? Right, next question. So without any filtering, a broadcast station at 1900 kilohertz is heard together with another station at 2800 kilohertz on a super heterodyne receiver. So they're saying a broadcast station at 1900 hertz is heard together with another station. What is the other station that we'll hear? Here they are interested to listen to 1900 hertz, which means they're talking about tuned frequency. 1900 hertz is the tuned frequency. What is the other frequency that we will listen to? The only frequency that we can listen to is the image frequency. The image frequency is 2800 kilohertz. Okay, they're asking us to find the IF, intermediate frequency. So the relation between Fi and Fc, I'll just revise quickly. If you take the local oscillator frequency as Fc plus IF, then image frequency will be Fc plus 2IF. Okay. If local oscillator frequency is Fc minus IF, then image frequency will be Fc minus 2IF. Okay. So local oscillator frequency can be any of these two. In the question, based on the data, you have to understand if they are using this local oscillator frequency or this local oscillator frequency. Or by based on image frequency also you can decide. Based on the relation between Fc and Fi. If Fi is greater than Fc, in this case, Fi is less than Fc. Based on the relation between Fi and Fc, or here, based on the relation between Fl and Fc, Fl is less than Fc, both the cases. In the first case, Fl is greater than Fc and Fi is greater than Fc. In the second case, Fc is greater than both Fi and Fl. Correct? So, in the given question, based on the information, you have to figure out whether they are using the first case or the second case. In the question, there is no information telling us whether they are using the first case or second case. By default, you can go with the first case. There is no sufficient information saying which of them they are using. You can go with the first case. Right. So you can observe that Fi and Fc, the relation is Fi is greater. Fi is greater means they should be using the formula Fc plus 2if. Correct? They should be using Fc plus 2if. Then only Fi will be greater than Fc. Right? Which means Fc we know. You can substitute Fc is 1900. So 2if is equal to Fc on the other side, 2800 minus Fc. Fc is 1900. 2800 minus Fc is minus 1900 is, what is that? 900 kilohertz. Fc is 1900. I'm substituting it here. So 2if will be 900. So if will be equal to 450 kilohertz. Correct? So 1900 plus 2 times 450 is 2000. So if should be 450 kilohertz. Simple question. Let's move on to the next one. A double-tuned amplifier used in a super heterodyne receiver has uncoupled tuned circuits with quality factor Q equal to 100 each, which means they are using two tuned circuits. When they are using two tuned circuits, I'll talk about it. A signal frequency 100 megahertz and the IF is 10.7 megahertz. The local oscillator frequency at the mixer is greater than incoming signal frequency. Incoming signal is nothing but tuned frequency, Fc, which means they are giving information that FL is used as Fc plus IF, not Fc minus IF, Fc plus IF, and the image frequency will be Fc plus 2IF. Find the image frequency of the receiver. So what is the image frequency of the receiver? Image frequency is tuned frequency, which is 100 megahertz, plus IF is 10.7. This 2 times 10.7 is 21.4 kilo, 21.4 mega, which is 121.4 megahertz. Is that okay? So that is the answer. Let's move on to the next question. Right. I think same data. Local oscillator frequency at the mixer is greater than incoming signal frequency. Same data. FL is greater than Fi. FL is greater than incoming signal frequency Fc. This implies FL, local oscillator frequency, is Fc plus IF, and that is what they're asking us. Local oscillator frequency they're asking us. Fc is 100 mega and IF is 10.7 mega, which is 110.7 megahertz. Okay, next. Image rejection ratio. What is the image rejection ratio? Image rejection ratio, we know the formula for image rejection ratio is root of 1 plus rho square into q square. That is when only one tuned circuit is there used. If there are uncoupled tuned circuits, which means two tuned circuits they are using, then the formula will be 2 times, multiply the same factor twice, rho square into q square. If the q is different, you can write as q1 and q2. If the q is same, you can write it as just q1. So it will be 1 plus rho square into q square. If you can remove that 1 also, because that will not change the value much. Okay, 1 plus rho square into q square is the answer that we have to find. Q is given as 100, so rho we have to find. What is rho? Rho is given by image frequency divided by tuned frequency minus tuned frequency divided by image frequency. Image frequency we found in the previous slide itself. It is 121. What is that? 120.1.4 divided by signal frequency is 100 minus 100 divided by 121.4. 1.214. Can you calculate it and tell me the rho value? Divided by 121.4 minus 0.39. Yeah, got it. It's a 0.39, something like that, approximately something like that. So 0.39 square 0.1523, something like that. So rho square is 0.1523, roughly around that number. So rho square 0.1523. If you multiply with q square 100, which is 10 power 4, you multiply with this, it becomes 1523, somewhere around that. So local oscillator frequency is 110.7. There are two options with 110.7. So 1521 is the closest number that we can get for image rejection ratio. So option A is the correct answer. Right? So I've covered pretty much most of the models of questions possible from analog communication, along with the concept revision wherever it is necessary. Right? So I'll conclude at this place for today's session. Right? So I hope this session was useful for you guys. Take care. Good night. We'll meet again in the next session.